Stuck doing nested BFS from every cell? O1 matrix is the perfect test of multi-source BFS thinking. It shows up often in Phong screens because a brute force approach explodes, while the optimal solution is beautifully simple. Start from all zeros at once and ripple outward. Let's crush it with basics so you can narrate it confidently. We're given an MXN grid of zeros and ones. For every cell, return the distance to the nearest zero using 4 directional moves. Distances are shortest path lengths in an unweighted grid. Brute force, running BFS from each one, is O, MN2. Instead, think backwards. The nearest 0 to a 1 is discovered if we start BFS from all zeros simultaneously. That's multi-source BFS. Push all 0 positions into the queue with distance 0. Mark ones as, or unvisited, then relax neighbors. Complexity, OMN time and OMN space. Alternative, 2 pass DP sweeping top left bottom right then reverse. High-level steps, initialize a dist grid. Put every 0 into a queue with distance 0. Set every 1 to inf, BFS. Pop a cell, try 4 neighbors. If dist near NC, greater than dist RC, plus 1, update an in queue. When the queue drains, dist holds the nearest 0 distance for every cell. Solution 1, multi-source BFS. We import deck to use an efficient queue for BFS. We define the solution class that will contain the method. This function returns the distance of each cell to the nearest 0. We store the number of rows and columns. We initialize a distance matrix filled with none to mark unvisited cells. We create a queue to perform BFS. We loop through all rows. We loop through all columns. If the current cell contains a 0, it becomes a BFS starting point. We mark its distance as 0 immediately. We add this 0 cell to the queue. We begin BFS, processing cells level by level. We take the next cell whose distance is already known. We explore the 4 possible directions. We compute the neighbor's coordinates. We check that the neighbor is inside the grid and hasn't been assigned a distance yet. We assign the neighbor the shortest possible distance, 1 more than the current cell. We add this neighbor to the queue so BFS can continue spreading. Finally, we return the fully populated distance matrix. Here the grid has zeros everywhere except the center cell, which is 1. We want each cell's distance to the nearest 0. All the edge cells are already 0, so their distance is 0. The middle cell is directly adjacent to zeros on all 4 sides, so its nearest distance to a 0 is 1. The output matrix matches the expected distances exactly, so our update matrix implementation is working correctly for this test case. Solution 2. Dynamic programming. 2 passes. This function computes the distance from each cell to the nearest 0. We store the number of rows and columns. We create a distance matrix filled with infinity, meaning distances are unknown. First pass, top left bottom right. We loop through each row. We loop through each column. If the cell is a 0, its distance is 0 immediately. If it's a 1, we try updating using neighbors we've already visited. We check the top neighbor. Distance may improve using the top cell. We check the left neighbor. Distance may also improve using the left cell. Second pass, bottom right top left. Now we go backwards through the rows, and backwards through the columns. We check the bottom neighbor. Distance may improve using the bottom cell. We check the right neighbor. Distance may improve using the right cell. We return the completed distance matrix. Our multi-source BFS pushes all zeros into the queue. BFS expands outward. 0 stays 0. Center 1 checks neighbors, finds a 0 distance 1. Final distances fill in perfectly. The algorithm correctly computes the shortest distance from each cell to the nearest 0, efficient, accurate, and reliable. Here the grid has zeros in the top 2 rows and a full row of 1s at the bottom. We're computing how far each one is from the nearest 0. The first 2 rows already contain zeros, so their distances remain 0. The bottom left one touches a 0 above it distance 1. The bottom middle one also touches a 0 above it distance 1. The bottom right one is 2 steps away from the nearest 0 distance 2. The result matches perfectly. The DP passes correctly compute the minimum distances for all cells. Center 1 closest 0 above distance 1. Bottom one's closest 0 either directly above or diagonally distances 1 or 2. Final distance matrix. 0, 0, 0, 0, 0, 1, 0, 1, 2, 1. The program outputs 0, 0, 0, 0, 0, 1, 0, 1, 2, 1, matching the expected result. The algorithm efficiently computes the shortest distance to the nearest 0 using multi-source BFS, accurate and reliable. Let's have a quick recap. Breakdown recap. We need the distance of each cell to the nearest 0 in a grid using 4 directional moves. It's all about finding shortest paths in an unweighted matrix. Assess recap. Instead of BFS from everyone, mn squared, use multi-source BFS, in-queue all zeros with distance 0 and expand outward. Everyone gets its nearest zero naturally in OMN. Structure recap. Initialize a distance grid. Add all zeros to the queue with distance 0. BFS outward. If a neighbor's distance can improve, update and in-queue it. Implement recap. Use deck for fast queue ops. Ran the multi-source BFS once. Clean, efficient, error-free on LeetCode. Check recap. All test cases passed. Distances matched expected results. Think in reverse. Start from known points and spread out. That's the power of multi-source BFS.